A white powder is analyzed and found to have an empirical formula of P2O5. The compound has a molar mass of 283.88 grams per mole. What is the compound's molecular formula? Well, I know its empirical formula, so it's pretty easy to find the molecular formula, right? Remember what empirical formula is. Empirical formula is defined as the lowest whole number multiple ratio. Which means molecular formula can be equal to empirical formula or a multiplet of the empirical formula. So let's figure out the mass of the empirical formula. P2O5, I've got 2 phosphorus, so 2 times 30.97 grams per mole, 5 oxygen, 5 times 16.00 grams per mole, and when I add this up, I get a total mass here of 141.94 grams per mole. I see the actual molecular formula, whatever I'm trying to find at least, the overall compound has a molar mass of 283.88 grams per mole. So clearly bigger than what I'm looking at. I'm going to take that molar mass, 283.88 grams per mole, and divide it by the molar mass of my empirical formula, 141.94 grams per mole. Gives me a ratio of 2. Remember, what does this tell you? This is telling me that my molecular formula is double that of my empirical. So that means, while my empirical formula is P2O5, my molecular formula would be double that at P4H10. You can always double check your work here. If you add up the molar mass of P4O10, you should find that it is in fact 283.88 grams per mole. What about number 2? A chemist decomposed the following sample. Determine the empirical formula and name of a compound containing 1.651 grams of silver and 0.1224 grams of oxygen. Okay. I've got both pieces, so I just need to figure out the mole of each piece. I know how many grams I have of each thing already, so it's even easier to do. I'm going to find the number of moles of silver first, just because it's listed first. 1.651 grams of silver. 1 mole of silver weighs 107.9 grams. This gives me a number of moles of 0.0153. And do the same thing for my oxygen. Number of moles of oxygen. I'm told I have 0.1224 grams of oxygen. 1 mole of oxygen weighs 16 grams. This is going to give me 0.00765 moles of oxygen. Remember, what I'm looking for is the empirical formula. And empirical formula is defined as the smallest whole number mole-to-mole ratio. Which means I need a ratio of the elements to one another, but I want the smallest ratio, which also tells me a lot of information. It tells me I'm going to be dividing by the smaller of the two numbers to get whole numbers, but I'm also going to be dividing so I can get that ratio and compare them. I look at these two numbers and I see that the number for oxygen is smaller, so I'm going to divide the silver by the oxygen. 0.0153 moles of silver is present for every 0.00765 moles of oxygen. This gives me 2 moles of silver, or sorry, 2 silver, because the moles cancel, to every 1 oxygen, meaning my overall formula is Ag2O. I have 2 silvers for every 1 oxygen. What's next? A chemist decomposed the following sample, determine the empirical formula and name of the compound. Naming is also a good thing here. This is called silver oxide. Remember, silver only has 1 charge. Silver is always +1. Therefore, I don't have to emphasize that it's silver 1 here. It has to be silver 1. and that is not always the case. In some species, we will have to emphasize the name. Okay, what do I have here? I have 2.677 grams of barium and 3.115 grams of bromine. So how many moles of barium do I have? 2.677 grams of barium. I look up barium in the periodic table because I definitely do not know that one. And I see barium has a molar mass of 137.3 grams per mole. Calculate this out and I get 0.01950. Notice I have 4 sig figs, so I'm adding an extra 0 to keep my sig figs right now. Moles of barium. We do the same thing for bromine. Number of moles of bromine. I have 3.115 grams of bromine. 1 mole of bromine weighs 79.90 grams. Again, from the periodic table. Calculate this out, and I get 0.03899, keeping those 4 sig figs, moles of bromine. But again, I want empirical formula. Empirical formula is the smallest whole number multiple ratio. So I'm going to divide both of them by the smaller of the two numbers. In this case, that would be the barium. So I've got 0.00389 moles of bromine for every 0.01950 moles of barium. And I get an answer of 2 here. I have 2 bromine for every 1 barium. So my formula, BaBr2. Notice on the previous example and this example, I'm listing the metal first, then the non-metal. You could take it a step further and say your cation first and your anion second. That way, if you have a positively charged polyatomic cation, it still lists first. Okay, your cation always goes first, your anion always lists second. But I have BaBr2, and this is called barium bromide. So my empirical formula, BaBr2, and my name, barium bromide. I do not have to put a Roman numeral on barium because barium is an alkaline earth metal. It's in the group 2 column. So that means it has a fixed oxidation state of +2 when it is in its ionic form. Okay, the next one. When a 0.3546 gram sample of vanadium metal is heated in air, it reacts with oxygen to achieve a final mass of 0.6330 grams. Calculate the empirical formula of this vanadium oxide. Okay, so I've got some kind of vanadium compound reacting with oxygen, and it's forming some compound. I just don't know what this ratio is yet. Well, let's figure it out. What are my number of moles of vanadium here? I'm starting off with a 3.546 gram sample of vanadium. I look at my periodic table and I see that vanadium has a molar mass of 50.94 grams per every mole. This gives me number of moles of 0.00696 moles of vanadium. But how am I going to find that mass of oxygen? Law of conservation of mass. I know my final sample is 0.6330 grams. I know that 0.3546 grams of that had to come from vanadium. Law of conservation of mass tells me if it went into the reaction, it had to come out, which means the remainder here, 0.2784 grams, had to be due to oxygen. So that's how much oxygen was reacted. So I can find my number of moles of oxygen. 0.2784 grams of oxygen. Convert to moles of oxygen. This gives me 0.0174 moles of oxygen. Now I've got, again, I'm trying to find the empirical formula, so I've got to find that ratio there. And I see that my vanadium moles are smaller than my oxygen moles. So 0.0, 0.17. Let's see, 0.0174. Let me check that. We should definitely have one more sig fig there. 0.2784 divided by 16, 0.01740 here. Moles of oxygen divided by my vanadium. Vanadium should also have more than one more sig fig. Let me check what that would be. There should be a 1 right there. Point 0.006961 moles of vanadium. And this gives me a ratio of 2.5 oxygen to every 1 vanadium. But again, I need whole numbers here. I can't have fractions. So what I'm going to do is I'm going to multiply this reaction by some factor to get a whole number. So 5/2. That means I have 2 vanadiums for every 5 oxygens. Again, when you see the 0.5, you're often multiplying by 2. If you see 0.3 or 0.67, you're usually multiplying by 3. If you see 0.125, you're multiplying by 4. 0.125, you're multiplying by 5. You're going to start to see the patterns there. So this is vanadium V2O5. So what would that be called? Well, the oxygens here each have a -2 charge. So overall, the oxygen is -10. There's 2. So again, 5 oxygens at -2. So an overall -10 charge. I have 2 vanadiums that have to add up to a +10 charge, which means this has to be vanadium 5 oxide. It didn't ask for the name, but if you did need the name, that's a common question as well. It would be vanadium. Calculate the empirical formula for the stimulant listed based on elemental mass percent composition. It's caffeine. So it's got 49.48% carbon, 5.19% hydrogen, 28.85% nitrogen, and 16.48% oxygen. Remember, when you're given percentages, assume 100 grams of sample. We do this because then we can use those percentages for mass. That means we would have 49.48 grams of carbon in the sample, 5.19 grams of hydrogen, 28.85 grams of nitrogen, and 16.48 grams of oxygen. Now we just got to find the moles of each species and then do a comparison. So my number of moles of carbon, I have 49.48 grams of carbon. One mole of carbon is 12.01 grams. This gives me sorry, my notes are really small, 4.120 moles of carbon. Do the same thing for hydrogen. My number of moles of hydrogen, I've got 5.19 grams of hydrogen. 1 mole of hydrogen weighs 1.008 grams. And this gives me 5.15 moles of hydrogen. Notice the 3 sig figs because I only had 5.19% grams of hydrogen, which is 3 sig figs. Number of moles of nitrogen, 28.85 grams of nitrogen. 1 mole of nitrogen weighs 14.01 grams. And this gives me a numerical value of 2.059 moles of nitrogen. And our number of moles of oxygen, 16.48 grams of oxygen. 1 mole of oxygen weighs 16 grams. So this gives me a numerical value here of 1.030 moles of oxygen. So now I have the moles of each species. Now I just need to compare them. Look at all of them, find the smallest number. And I find my smallest number is oxygen. My smallest number of moles of oxygen. So I'm going to compare everything to oxygen. So for carbon, 4.120 moles of carbon to 1.030 moles of oxygen gives me a value of 4 carbon to every 1 oxygen. Hydrogen, 5.15 moles of hydrogen to every 1.030 moles of oxygen gives me a number of 5. So 5 hydrogens to every 1 oxygen. Again, that's an oxygen, not a 10. And nitrogen, 2.059 moles of nitrogen to every 1.030 moles of oxygen gives me a value of 2. So 2 nitrogen for every 1 oxygen. I see here that I have 4 carbons, 5 hydrogens, 2 nitrogens to every 1 oxygen. So my empirical formula for this stimulant, C4H5N2O. Calculate the empirical formula for stimulant listed based on the elemental percent composition for nicotine. Here I've got carbon, hydrogen, and nitrogen. Again, because we're given percentages, we're going to assume 100-gram sample. This gives me 74.3 grams of carbon, 8.70 grams of hydrogen, and 17.27 grams of nitrogen. First up, find the moles of each species. I start with carbon just because it's listed first. 74.03 grams of carbon. 1 mole of carbon is 12.01 grams of carbon. This gives me 6.16. Hold on, 6 here. See 74.03 divided by 12.01, 6.164 moles of carbon. Looking at hydrogen, I have 8.70 grams of hydrogen. 1 mole of hydrogen is 1.008 grams. Gives me 8.63 moles. And my nitrogen. Number of moles of nitrogen, I have 17.27 grams of nitrogen. And 1 mole of nitrogen weighs 14.01 grams. And let me calculate that. 17.27 divided by 14.01 gives me 1.233 moles of nitrogen. Look at all the numbers, and I see nitrogen is definitely the smallest of the numbers. So I'm going to compare everything to that. 6.164 moles of carbon to every 1.233 moles of nitrogen. Gives me 5 carbon to every 1 nitrogen. And 8.63 moles of hydrogen to every 1.233 moles of nitrogen. Gives me a value of 7 hydrogens for every 1 nitrogen. So that means empirical formula, I've got 5 carbons, 7 hydrogens to every 1 nitrogen. Again, does that mean that's the actual molecular formula of nicotine? I don't know. I don't know what the molecular formula is. I do know this is the empirical formula. It's the smallest whole number ratio of the compounds to one another. Next up, an unknown compound contains the following percentages by mass: 60.86%, 5.83%, 23.16%, and 10.14%. Determine the empirical formula. So again, because I'm given percentages, I'm going to go ahead and assume 100-gram sample. So my number of moles of carbon, 60.86 grams of carbon. One mole of carbon to 12.01 grams of carbon gives me 5.07 moles of carbon. Let's see, what's next? Hydrogen. Number of moles of hydrogen, 5.83 grams of hydrogen. One mole of hydrogen is 1.008 grams. This gives me 5.78 moles of hydrogen. Next up is my oxygen. Number of moles of oxygen, I've got 23.16 grams, because again, I assumed 100-gram sample, so my percentages turn into grams. One mole of oxygen is 16 grams of oxygen. Gives me 1.45 moles of oxygen. And lastly, nitrogen. I have 10.14 grams of nitrogen. And one mole of nitrogen weighs 14.01 grams, which gives me 0.724 moles of nitrogen. So now I got to compare them all. I look at all of them and I see that, let's see what color am I not using right now. I use this. I see that nitrogen has the smallest ratio, the smallest number of moles, I mean. So I'm going to use that to find my ratios. So for carbon, I've got 5.07 moles of carbon to every 0.724 moles of nitrogen. This gives me a value of 7. What that means is 7 carbon for every 1 nitrogen. Hydrogen, I've got 5.78 moles of hydrogen to every 0.724 moles of nitrogen. This gives me a value of 8. So what that means is 8 hydrogen for every 1 nitrogen. And I've got 1.45 moles of oxygen to every 0.724 moles of nitrogen. This gives me a value of 2. So that means 2 oxygen for every 1 nitrogen. So I've got 7 carbons, 8 hydrogens, 2 oxygens to every 1 nitrogen. C7H8O2N is my empirical formula. Let's see, cisplatin, the common name for a platinum compound that is used to treat cancerous tumors, has the mass composition of 65.02% platinum, 9.34% nitrogen, 2.02% hydrogen, and 23.63% chlorine. Calculate the empirical formula for cisplatin. Okay, given percentages again, so I'm going to assume 100 grams again. That means I can quickly go to my number of moles of each species. My number of moles of platinum. If I assume 100 grams, that means I have 65.02 grams of platinum in my sample. I look it up on the periodic table and I see that platinum has a molecular weight of 195.1 grams of platinum to every 1 mole of platinum. This gives me an answer of 0.3333 moles of platinum. Do the same thing for nitrogen, hydrogen, and chlorine. So my number of moles of nitrogen, 9.34 grams of nitrogen. I know 1 mole of nitrogen weighs 14.01 grams because that's from the periodic table. And this would give me 0.667 moles of nitrogen. Next up, hydrogen. Knowing number of moles of hydrogen, 2.02% means 2.02 grams in a 100-gram sample. Notice here, it's just hydrogen atom, it's not H2. H2 is a diatomic, so hydrogen is a diatomic when it's reacting. When I'm doing empirical formula, remember, it's just single hydrogen. 1.008 grams of hydrogen for every 1 mole of hydrogen. This gives me 2.00 moles of hydrogen. And my chlorine, number of moles of chlorine, 23.63 grams of chlorine. Every 1 mole of chlorine weighs 35.45 grams. Again, chlorine is a diatomic when it's reacting, but right now I'm doing the empirical formula analysis, so just the atoms of chlorine, not a molecule of chlorine, okay? This gives me 0.6667 moles of chlorine. So let me move these down a little bit. When I look at all my numbers here, I see platinum is definitely the smallest of the numbers I have. So I'm going to compare everything to platinum. So for nitrogen, 0.667 moles of nitrogen to 0.3333 moles of platinum gives me a value of 2. Hydrogen, 2.00 moles of hydrogen to every 0.3333 moles of platinum gives me a value of 6. Again, what does that mean? That means 2 nitrogen to every 1 platinum, 6 hydrogen to every 1 platinum, and chlorine, 0.667, sorry, 6667 moles of chlorine to 0.3333 moles of platinum. Gives me an answer of 2, but what does that mean? That means 2 chlorines for every 1 platinum. So my overall formula here, I put metals first. So platinum, 2 nitrogen, 6 hydrogen, and 2 chlorine. The empirical formula of cisplatin, PTN2H6Cl2.